Howdy! This is a presentation on the analysis of hydraulic fracture test Site 2 dataset. The project was initially hosted and operated by Anadarko Petroleum Corporation and then Occidental Petroleum Corporation after their acquisition of APC in 2019. Oxy is the current host and operator for the Hydraulic Fracture Test Site 2 project. Hydraulic Fracture Test Site 2 is about 140 miles west of Hydraulic Fracture Test Site 1. These images illustrate the location of Hydraulic Fracture Test Site 2 in Loving County, Texas, Block 55. On the far right image is a plan view of the two existing parent wells and 8 new horizontal wells, including 2 new science wells. The vertical and slant well are indicated as red dots. The Hydraulic Fracture Test Site 2 project is managed by GTI with DOE being the primary sponsor and NETL administering and managing the project for DOE and performing specific research. GTI is also responsible for the project and specific research ranging from proppant analysis to data integration. Industry members provide cost sharing to the project in the form of cash or in-kind contributions. Occidental is the test site host and is responsible for managing day-to-day field operations of the test site, including management of vendors and subcontractors for field and laboratory work. The following figures show a detailed project structure and roles, 6 technical subcommittees, and all industry members. 6 technical subcommittees were created to provide technical input and direction for specific areas of the project. The subcommittees comprise members from DOE, NETL, GTI, the test site hosts, and all industry members. The pilot hole is a vertical hole drilled to Wolfcamp B formation, and 4 vertical core sections were obtained from the Third Bone Springs formation through the Wolfcamp B. By various labs and vendors, approximately $1.5 million was utilized in core analysis. This is an image of the depths of various formations and the location of the vertical cores taken in the vertical pilot hole. The location of the cores is the first track from the left. The location of sidewall rotary cores is the second track from the left. The location of PT gauges is the third track from the left, and boxwood well locations are the fourth track from the left. The objective of the slant well is to sample the graded fractures and to monitor reservoir depletion. To this end, a slant core well was drilled closely to the horizontal producer. It was drilled from the same pad at the surface as the pilot hole. A total of 949 feet of 3-inch diameter core was recovered from 9 core runs in the slant well. Cores 1 through 6 captured rock intervals above the nearby stimulated well, and cores 7 through 9 were from below it. The team followed established fracture description methods as described and deployed in the previous Hydraulic Fracture Test Site 1 project in the Midland Basin. Hydraulic Fracture Test Site 2 demonstrated advanced FO technologies for stimulation and production monitoring. In the Hydraulic Fracture Test Site 2 project area, fiber optic cable was permanently installed in 2 horizontal child wells and 1 vertical well. This unique 3-well design enables spatial and temporal hydraulic fracture propagation and production depletion monitoring. This is the first project which utilizes 3 fiber optic wells, including a vertical and horizontal well, to collect FO data. There are 2 kinds of data obtained from this fiber: near wellbore survey, which measures the response from the activity in the fiber wells, and far field survey, which measures the response from the activity in the offset well. This image illustrates the applications of FO technologies at Hydraulic Fracture Test Site 2. The red lines and dots represent the fiber wells, and the non-instrumented wells are indicated in blue. Through near wellbore surveys, distributed acoustic sensing and distributed temperature sensing data were acquired during the stimulation of two horizontal fiber wells. Through far-field surveys, cross-well strain data were acquired using low-frequency DAS to monitor response on the fiber wells to activities on the offset wells. The objective of microseismic monitoring is to estimate SRV and integrate observations with other diagnostic techniques to understand well and reservoir interactions better. The conventional microseismic dataset that was acquired during stimulation of the Boxwood 1, 2, and 4 was designed to help understand the fracture geometry in the presence of multiple new wells and nearby depleted zones from legacy wells. 5 static arrays are displayed in the figure on the left to ensure that interpretation and processing for all 3 wells would remain consistent. The figure on the right shows the microseismic results for all wells colored by frac stage number. The microseismic data indicates there is a strong influence of depleted areas pushing microseismic activity towards the depleted zones caused by production of legacy Bitterroot wells. The pressure reading obtained in the Hydraulic Fracture Test Site 2 dataset were used to quantify the impact of frac hits and depletion. Analyzing all the gauges during stimulation, we observed that the frac hit severity increases as we go to the shallowest gauge, indicating the preferential upward direction of fracture propagation. The pressure drops seen in the gauges in the vertical well during production show the depletion in each of the benches except Wolfcamp B, which confirms that fractures don't grow downwards. These pressure measurements were confirmed by the measurements from the slant well. Comprehensive and integrated diagnostics associated with the design of the experiment enabled a unique opportunity to evaluate stimulation distribution effectiveness, evaluate the created fracture geometry domains, and evaluate the effective inflow and depletion domains. The goal was to improve stimulation distribution effectiveness. Based on the statistical analysis of hydraulic fracturing profiles with effective limited entry practices, rate per cluster during proppant slurry placement appears to be a primary completion design variable rather than rate per perforation, which is the typical default consideration. Also, based on near-field DAS and DTS data, completion operational issues add the risk of degradation of SDE.
Hydraulic fractures for the Boxwood wells are modeled using the ResFrac Pro hydraulic fracture simulator. A black oil model is employed. Wells are created with information from their respective directional survey. The hydraulic fracture model is scaled down to one stage to be computationally valid, and the fracturing fluid used is a standard slick water with a proppant mixture of 40, 70, and 100 mesh.
ResFrac's simulator is utilized to obtain high-quality results when hydraulically fracturing. It is physics-based and solves the governing equations of fracture mechanics, proppant transport, fluid transport, and geomechanics. It is a true fracture simulator which meshes the cracks as cracks and uses fracture mechanics and equations for transport in a crack. This software delivers more accurate results and better optimization of well performance. Multi-stage hydraulic fracturing is a good technique to improve production from low permeability reservoirs. The objective is to increase the surface area of the reservoir in contact to the wellbore. Proppants help keep high conductivity in the newly created fractures. The main site-specific takeaways are as follows. Fractured descriptions of the slant core provided a better understanding of geometry and spatial distribution of hydraulic and natural fractures in the SRV. Aerial coverage of hydraulic fractures from diagnostics and simulation results indicated connections between child wells during stimulation. The workflow presented here is not limited to the given area or formation. It can be applied to improve understanding and optimize fractured well performance for most unconventional fields. Thank you for listening to this presentation on the analysis of hydraulic fracture test Site 2 dataset. More details are found in the paper.